All right, so now we've taken our full theory 3-point amplitude, we expanded it, we found the 2-point amplitude times this iconal factor, and we found this multiplicative structure. So we've learned something, right? That when we want to go from a configuration of 3 partons that is almost degenerate with my configuration of 2 partons, then this is the form of the amplitude. This is where it goes, up to some corrections that I currently don't care about. Now, we want to build an operator that reproduces this. In particular, I'm going to write limit as P3 goes soft. And 1, 2, and 3. And there's going to be some normalization. So I have some hard collinear operator. And I want to figure out what this O hat hard collinear and this O soft operators actually are. I'm doing this in a particular matrix element, but once I have figured out what my hard collinear operator is and what my soft operator is, then I'll have this object. And this particular operator, and I write this cross mark here because in this cross mark, it's going to hide a multitude of sins, which are like contraction of color indices. If you really get down into the nitty gritty, there might be some convolution integrals in there, so on and so forth. But I'm just right now, I'm just going to have this sort of tensor symbol to mean there could be contractions of at least color. We know that at least there's going to be color because we can just look at this form here. I have dummy color indices here. I have the dummy color indices here. There's going to be a color exchange between my 2-point amplitude here and whatever was that soft factor multiplying it. But once I figure out what these hard collinear operators are in this soft operator, I'm going to argue that I should be able to figure out everything just based off of this 3-point amplitude, what these 2 operators have to be. But once I have those 2 operators, I could now start making these states here arbitrarily complicated. I can have additional soft radiation. I can have additional collinear radiation. And this operator will interpolate it all. So that this operator here will describe 2-jet X decays. Where 2-jet, I mean any particular amplitude like this, that taking matrix elements of that amplitude with this particular number of partons will reproduce the full theory amplitude up to power corrections in my soft and collinear expansion. I have this multiplicative form here because, I'm just learning, I'm just paying attention to this full theory expansion that I did. I already got a multiplicative form out, so I might as well keep that around. But we're going to first now focus on what this O soft is. And I know that this O soft needs to be built out of invariants, right? But it cannot be local invariants. Why can it not be local? Well, if I look at my expression for the expansion of the 3-point amplitude, and I ask, is this thing polynomial in my momentum P3? The answer is no, it is non-polynomial in my momentum P3. And the physicist shorthand should be local means you're polynomial in the momentum, right? So it's not polynomial in the momentum. I cannot have a local operator that will interpolate my soft field form, my soft matrix out of my form. And I can just get that by looking at the full theory expansion. So what sort of matrix, what sort of operator do I need? Well, I'm going to write down the answer. I already gave you the recipe for building non-local operators, right? So we could go through the song and dance where we try to discover what the non-local operator is, but that would take a very long time. Instead, I'm just going to now hand it to you by fiat and then try to motivate it based on some just physical reasoning. And technically, since these guys are in the adjoint, I don't think I can put it back, but I'll put it there. Now, these are my Wilson lines. They're meeting at the point 0. And they're traveling out. Sorry. In the direction of my two jets. Now, this is going to be gauge invariant because there are no gauge transformations at infinity. And the gauge transformation at 0 is being canceled between these two. So that's great. If I expand them out, I would have gotten this particular expression up here. I'm going to try something. Where's undo?
Undo. Top left, middle top left.
Yes.
Backwards arrow. Erase it. Get the loop, get the lasso.
On your left, it's the arrow. Isn't that arrow, curly arrow?
Yeah. No, I'm good now.
Okay. You want to lasso that?
No.
Yeah, you have to not include any text from the lines, not really going through the white space.
All right, well, lasso tutorial.
Yeah.
Right, there you go.
Yep. Yep. Ooh, you're not gonna
And don't let go.
on. Yeah.
Don't pause too long. Then it'll turn into a box.
You can just start to talk over. There you go. Keep going.
Got it.
Yeah.
You want to start?
You want to copy it?
Copy.
Yeah, you just copy it and you'll.
Okay,
Yeah.
click on it. Oh, there.
Yeah,
Copy
it is.
it.
Yep. You got it. You would have learned this if you had to teach during COVID.
All right, now I love paste.
Tap it, tap it in the white space.
Tap it with your finger,
No,
push down and paste.
Boom.
And you can move it still. Yeah, there you go.
All right, now modify this a little bit. I don't know if that actually saved me time.
I don't think so.
But it was fun.
Teach us physics, we'll teach you how to use my iPad.
Okay. So say I expanded for right now, this particular S, right? And I expanded to leading order in IG. Then the matrix element that I wish to take is this guy, right? And we'll cheat a little bit. We have S1 here. And then we have A, and we have S2 here and B. Those are the color indices that I had been suppressing up till now. So this would have the color indice of S1A. And you can go and you can grind through the calculation, but what you will find is precisely my iconal factor. That I had up earlier. Wonderful. And you can do a similar calculation with this SQ2, and you would find the exact same expression. Right? And why is that? Well, the physical motivation behind it is that I have my hard glue on Q1 going off in the Q1 direction. I have my hard glue on Q2. I have my other hard glue on going off in the Q2 direction. And as it goes, it's going to brim off soft radiation. And the soft radiation, since it's weak, is not going to change the path of my hard glue on at all. It's going to just only do minor perturbations to my path. So I can ignore those perturbations up to some leading power expansion and say that it doesn't move at all. It just completely absorbs the recoil from this soft radiation. And what my Wilson line is describing for me is, all my insertions of A along my Wilson line is telling me how that soft radiation got created as my hard gluon moved off in the Q1 direction or the Q2 direction. So that's sort of the physically motivated reasoning behind it. I know to look for an operator like this because of two things. One, I looked at the expansion and I realized it could not be local. And two, I went through that long song and dance telling you how to build non-local invariants. So once you know how to build non-local invariants, you just start go hunting, right? And what should you hunt for? Well, we can just use a little bit of reasoning. My non-local invariant should depend on the direction Q1 and it should depend on the direction Q2. And I know that things should be Wilson lines. Therefore, I should look for a Wilson line that depends on Q1 and Q2. And why is it straight? Well, it's straight because I don't really care about the small perturbations. Those small perturbations in the soft limit are not going to deflect things off of the path that it's traveling. And so that would be the reasoning you would go through in order to figure out what this soft operator had to be. So great. We now know what the soft operator is, and that gives us tremendous power. Because I figured out what that soft operator is with just one emission. But now I can dress this thing with an arbitrary number of emissions, and it will describe them all at leading power. And that's why we wanted to find this operator formulation. Because it's going to allow us to do all of the degenerate states that preserve the 2-jet configuration. In other words, it's going to capture for us the entirety of the weak perturbations around the ground state of my theory. So that was the easy part. Now I have to deal with my hard collinear matrix element. And immediately I'm going to see something. I have some operator, I have a vacuum. So I need something that's going to destroy these two states, right? And what destroys a state? Well, you know, a mu of x can destroy a state, but a mu of x is evil.
Should you be creating?
I'm sorry, creating a state. Yes,
That should be flipped.
it should be flipped.
I'm not gonna mention it. Right.
I use Hebrew when I perform quantum mechanics. A mu is evil. D mu, I mean, my F mu nu is not much better. Because,
What do you mean by A mu is evil?
well, because if you write down the gauge transformation properties of A mu, it's a disaster, right? F is a little better because it's now just a matrix multiplying it, but it's only less evil.
Yes.
So these are the type of operators I would like to use in order to create or annihilate states, but they're not gauge invariant, so I'm gonna have to figure out something to do with them, right? But to get there, I'm going to need collinear power counting. So up till now, I've been able to play fast and loose with the power counting. I said P3 is soft, and I didn't really assign a power counting to it. I just said it was soft and these invariants are getting smaller. And this is actually an interesting thing about the soft sector. You can assign almost any power counting that you want, and at this level of amplitude factorization, you'll never see a difference. You can say that your soft is going soft as some parameter lambda goes to 0. Or it goes soft as lambda squared goes to 0, or lambda to the 40th goes to 0. And at the amplitude level, you're never going to see a difference between those two. You're going to come up with the same structure of Wilson lines, regardless of how you do your soft power counting. When are you going to start seeing differences between these different power countings for soft radiation? And by lambda, I just mean lambda is some number which is much, much less than 1, and say, my invariant P3, P1 is order lambda of some power A. That's what I mean by it's going soft. And same for the other invariant when I do P2 on top and bottom. Like that. This A exponent could be 1, it could be 2, it could be 40. Whatever I assign it, I would have gotten the same Wilson line structure at the amplitude level, and I'll never see a difference between them. You will see a difference between these power countings Monday when we actually do TMD factorization. It'll matter how we say the soft radiation goes to 0. And it will radically transform what our theory is. And by I say you won't see a difference, I really mean you won't see a difference to leading power. Even at the amplitude level, if you get into the nitty-gritty of SCET, once you go into subleading power, then you start seeing that the scaling of your soft radiation actually does matter. And you would write down different subleading power Lagrangians depending upon the power counting that you assign to your soft radiation. But right now, we're just doing leading power stuff. We're not going to worry about such complications. All right. So how are we going to do our collinear power counting? Let lambda be some number which is really small. And we're going to introduce some energy scale Q. In our Higgs decay, we should think of Q as being close to the Higgs mass, but it's some just energy scale Q. Another thing we could think of Q squared as being on the order of P1 by P2. Or, sorry. So the hard configuration that we're expanding upon. Then momenta P1, P2, Pk are collinear to null direction in with conjugate in bar if a squared bar squared 0. This is mainly, so that everyone knows my conventions. B, any of my momenta, I equals 1, okay. Can be broken up into my lead coordinates. Like so. And I have the following scalings. So that's what I mean by that set of momenta is collinear. That they all follow that particular type of scaling. What does that imply about that set of momenta? Well, any dot product between the two, you can easily convince yourself that this is order Q squared lambda squared. In particular, both of these is order Q squared lambda squared. So in the dot products between Pi and Pj, there's nothing to expand. I have what's called homogeneous power count, which means that any propagator that I would see, which all roughly goes 1 over some k squared, where k is some momentum made up of my p1 pk. Some of those could be loop momenta. Any such propagator, 1 over k squared, there's nothing to expand. It's just what it is. What's important is that as lambda goes to 0, this is becoming on shell. And as lambda goes to 0, if I demand that Q1 approximately equals P1 plus ... pk, then I haven't really changed my overall momentum configuration for my 2-jet state. In other words, my allowed cone size is of order lambda. So everything inside that cone is summing up to my Q1 approximately, up to, corrections, which goes order beyond that.
What did you say about 1 over k squared?
Oh, if K is some subset of my collinear momentum,
Right.
this has homogeneous power. In other words, right, I'm going to get my collinear singularities in my in the loop diagrams that I would do like in my collinear sector, right? And they would match the collinear singularities that I would have in full QCD because those propagators aren't being expanded. They're homogeneous in the power. So now, when I introduce some subset of momenta, which are all collinear to each other, in order to do that, I've given myself 2 directions, n and n bar, right? As soon as I have directions, that means I can start building non-local invariants. In particular, though, I need to transform this sort of rule about what I call momenta to be collinear into a power counting on operators that I might want to write down, which are going to interpolate these collinear momenta. So how do I get momenta? Well, I take derivatives, right? If I have some operator and I take its derivative, then if I Fourier transform that, it's just going to be multiplied by the Fourier variable that I introduced. So in some sense, that is going to be a momentum. So O hat is a collinear operator. If when I take its covariant derivative contracted into the n bar direction, this will be order Q in my power counting. This will be order Q lambda squared in my power counting. Times whatever is the order of my operator itself. Right. So if my operator was order 1, then it would just be order Q. If my operator is already down by several powers of lambda, then this thing is just at the same order as my original operator. Sorry. All right. So immediately you should be troubled. Pop quiz, why are you troubled? Come on, guys. This derivative does not give me any power suppression. In other words, I can take my operator O, right? I can have an arbitrary function of that particular derivative, divide by my arc scale Q, which I have lying around. And this new operator that I've written down is exactly the same order as my original operator. Right? And so that's somewhat troubling. In other words, it looks like I've introduced this collinear power counting. I said I was going to introduce this collinear power counting to you in order to limit the space of possibilities. And already at leading power, it looks like I have an arbitrary space of possibilities that I can write down for my operators. Right? But we will fix this. How will I fix this? Well, I'll fix this with non-local operators. This particular derivative is associated with a particular direction, right? That immediately should bring to mind back to what our non-local operators are, which is our Wilson lines going off in a particular direction. In particular, there's one Wilson line, which I'm going to be most happy with, which I'll call W sub n, that obeys this particular property. When I take its covariant derivative, it's 0 in the direction of n bar. Immediately, if we go back to my discussion of the non-local, of building my non-local invariance, that tells me what this Wn needs to be. Now that I have this Wn, I can do something very interesting. Now, I haven't told you really where this Wn is coming from diagrammatically. I will in a moment. Right now, I'm just merely introducing it as being a particularly special operator because of my collinear power counting. It's special because it's the one operator that's going to suck up all of these possible covariant derivatives that aren't changing my power counting at all. Why is it going to suck them up? Because when I act on that thing, it goes to 0. It just kills it. Right? So if I build objects with my Wn and then I act with this particular covariant derivative, I'm not worried about making new operators because I'm just destroying them. Right? And it's sort of the unique object that can do this given the power counting that I've written down.
So it works the same on all the powers.
Yes. Now, physically, so if you go back way in time and you read CSS, what WN is. It's the remnant of the hard interaction that the collinear sector can know about. That's how you would build it up diagrammatically. In other words, if I had some hard interaction outshot my collinear sector in, I can have gluons that attach back into my hard interaction. And if I expand diagrams, according to this particular power counting right here, what you would find is that this entire hard interaction could be made up with this WN and just iconal connections to it. So that's for those who are more used to doing things in the CSS way, that's where you would find this WN. But I'm not finding it that way. I'm just writing down my collinear power counting. I'm noticing something odd about my particular covariant derivative, and therefore I'm introducing an object which gets destroyed by that covariant derivative, because then that means I'm not going to have an infinite number of those covariant derivatives anymore.
There's a Zoom question. Is it like a killing vector? But I don't know what it is.
A killing vector? No, WN is not like a killing vector.
You're not projecting out like conserved quantities.
Yeah, this is not a conserved quantity.
But you are using, it seems like you're using the same technique before we used V, the vector V is the direction.
Yes,
And here you're using this light cone vector,
yes.
N or N bar.
Well, so far I haven't used it to build anything gauge invariant yet, right?
I know, but it looks like you're using the condition that you're going along a path. This path is different than, I mean, this path is defined by the N vector
Yes,
rather than the V vector.
yes. And of course, it's sort of a terrible notation. The collinear Wilson line in the N direction is actually the path along the N bar.
Say that once again? Oh, yeah, yeah.
I have N here, but N bar shows up here, right? So it's
Think about it, it makes sense because the remnant of the hard interaction you talked about, everything else in a different point direction is
well,
approximated by F1.
yes. I mean, basically what I'm saying is that whatever the hard interaction is, to everything in the collinear sector moving in the N direction, it just looks like some collinear sector moving away in the N bar direction, because I'm traveling rapidly away from it. And any gluon sourced out of that is going to be built into this collinear Wilson line.
Are we going to talk further about proving that this is the only invariant, or do you have a comment on how to prove that WN is the only?
I'm not proving anything in this entire talk.
Fair enough. Well, let me ask you a question. So you said that, yeah, we're worried that acting with nbar.d
Yes,
is for all, none of them are power suppressed.
yes.
So how do we know that we don't need to worry about any other operators that have nbar.d's? So the things that you build out of W are things that you add an nbar.d.
Because I can now get rid of nbar.d entirely. This is going to be my next step.
Okay.
I guess I will show you the proof for this. Right.
So then asking is the next step.
Okay. So how now am I going to get rid of these nbar.d's? So if I have my arbitrary function of nbar.d, this will be true. In other words, my Wilson lines will enable me to get rid of my covariant derivative in nbar.d and make it a function of just my normal derivative. Sorry, that should be bar.
So I've seen this before.
All right.
I've never seen
Hopefully,
it proved. I've never seen it proved.
hopefully. Now,
Overflow.
technically, I'm only going to prove it for functions that are polynomials. So,
I'm sorry, before you go any further, can I just have a question about notation? N bar could have been just N, basically the important part is it's big D going to a normal partial D. That's
Yes.
really the heart of this, right?
yes,
So it's just, you chose N bar in this case, it could have been N, but basically this, the idea is that it's the N dot big D going to N bar partial D is just a matter of surrounding it by these Wilson lines coming in and out essentially. It's like sort of staple-like kind of thing in this case. So like this is not the V-shaped thing anymore. This is now out of it.
yes,
Okay, sorry, just trying to, sorry, thank you.
Yeah. it's out and in, or in and out. I mean.
Yeah.
So technically, all I'm actually going to show that the proof, because I didn't want to spend forever on it. I'm going to show that this is true if F is the identity operator. But if you show it's true for the identity operator, then the proof generalizes for anything that's actually some polynomial, right? Without any problem, because I can always insert a W and W dagger anywhere I want inside the polynomial. Okay, and then I can sum over polynomials, and then, you know.
Because W dagger W is unitary.
Yes,
Okay.
yes. This is most definitely true.
Other way around.
Yeah. So
Both are true,
Okay.
because you can dagger both sides.
But just in the way you're writing it, I think it's more.
Yeah. All right. We're going to prove this by checking it on some check on test operator. No comments from the peanut gallery. So I have my test operator O hat. I'm going to act with my covariant derivative. What is this? This derivative here, which is just a normal partial, is only acting inside these brackets. That's why I put those brackets there. And from now on, whenever you see brackets, that means derivatives only act to the right of whatever object is in that bracket and no further. This substitution right here is coming from the fact that this was true. In other words, I'm allowed to replace my gauge field for my partial derivative when I'm acting on my Wilson. So now I've just inserted 1 in front of this. Like so. Where now I'm just using Leibniz rule. Because in this above equation, I should always think of this F as acting on some test operator. Right? And so when I wrote down that earlier expression, I put a test operator here, I put a test operator here, and this function F is acting everything to the right when I have that test operator. So really, if I wanted to be precise about this statement, this is what I should have written all along. For every test operator that I could do.
So the proof relies on this capital,
Yeah,
which is the same thing you used before. When you were talking about solve.
it is, but now it's in the collinear section.
I understand.
The rest of the hard interaction is carrying away all my gauge theory troubles. Now we're going to start building operators. And what's going to be nice is that because of these Wilson lines converting our covariant derivatives into normal derivatives, it means that that normal derivative has no dynamics associated with it, and it means I can actually pull it back into the hard interaction. So any of these, and any normal derivatives like this, I can actually think of as being part of my matching coefficient. This is sort of the important point, the subtle point about constructing the collinear sector in SCET. You could go back and say, okay, Duff, you did some sleight of hand here, but look, this n bar dot d is still going to bring powers of q, and I can have arbitrary powers of q showing up because it's not giving me any power suppression. So, okay, you've traded problems in your covariant derivative for problems in your normal derivative. I don't mind problems in my normal derivative because my normal derivative only depends upon hard scales. It only bringing with me momenta that's of order q, which means it's tied to the hard interaction. I've gotten rid of my gauge field, so there's no dynamics associated with my normal derivative. It's always going to be a part of my matching coefficient. And that's how I'm going to solve that problem. How many normal n bar derivatives do I need? However many I need in order to make up the hard matching. Right, which will be the last piece of the puzzle that we get to.
Which is basically your ground state.
Which is my ground state.
And everything else is the perturbation.
Is the perturbation around it, exactly.
So what you're left with is the interesting stuff. The
Exactly.
wiggle or jiggle, or
Yeah.
whatever you want to call it.
So that's what was important about doing this little proof here, that I can get rid of covariant derivatives for normal derivatives in Wilson lines. The Wilson lines will factor into my collinear sector, and the normal derivatives will be part of my hard interaction, and calculating my hard interaction will tell me how many of those derivatives I need. So now we just need to build leading power operators. So my quark fields are easy. This is some sort of trace over my gauge indices that are at the point X. Remember, Wn is a Wilson line, so it has two gauge indices associated with it. One sitting off at infinity, it has no gauge transformation properties. The other one is sitting at X. The trace is over the one that's sitting at X, right? Because that's where I'm going to see gauge transformations, that's where I want to kill it. So this will still have an SUNC index, right? This will be some index I, and there'll be I, J here, and there'll be some J there. But this index does not change under gauge transformations because it's the index sitting off at infinity. So here's my operator, here's my Wilson line. It's going to create some state. My index I sits there. Which is nice because it's sort of the index that's associated with the rest of the hard interaction. Now, for my collinear fields, I just form And I'll do it this way. Mainly so that I don't have to introduce adjoint Wilson lines. Like so. I'll take my normal field tensor, which is going to create and annihilate some gluon. And then I'll dress it with these collinear Wilson lines, and I'll format my Bn. Now, this is not homogeneous. In my paragraph. I think I got the daggers correct. Good. How can we see that? Well, my stress tensor is just the commutator of my covariant derivatives. If I go back to these rules here, I'll find that my covariant derivatives have different orders associated with them. So depending on which components I take of my stress tensor, I'll get different objects, right? Up. I can do n bar n, that's actually power suppressed, because this goes as lambda squared. Right. So really I want to go n bar perp. In other words, I only care about transverse polarizations of my gluonic fields. Those are the leading power things. That operator will be ordered lambda. But you might say, but Duff, n bar, that's order 1. Yeah, but the commutator makes it 0. So I'm not worried about n bar. So I'll define where I'm only taking the transverse directions for my nu. So if I dot n bar into nu or n into nu, that will be 0. This thing, based on the power counting of my derivatives that I wrote down earlier, is this particular operator here is of order q lambda. And I put this derivative here so I didn't have to write down q squared lambda there. You could also see that inside these Wilson lines, when I do the n bar dotted into this d, those Wilson lines are actually going to make that d covariant into just a partial derivative. Right, and I'm just pulling that partial derivative out when I define this b perp operator.
Spending the power and making it a regular derivative.
Yeah. And here's something neat for those of you who are familiar in light cone gauge. If I said, I'm going to choose this gauge condition, I'm going to kill those Wilson lines that I built up. That will be true. I might actually have to put a G here, but up to some normalization I haven't looked up. But that will be true. And whenever you're doing factorization in light cone gauge, you always say that my gauge field, potential field, in the transverse plane is sort of the leading power operator that I'm interested in when I'm doing light cone gauge. And that's being just automatically produced for me by my power counting. And so in some sense, and in fact, if your name is Martin Binnicky, this is actually how you would build up SCET. You would first go to light cone gauge, write everything in light cone gauge, and then you move out of light cone gauge by putting Wilson lines where you need them to be. But those are my two leading power operators, right? Any further operator that I would write down is going to be power suppressed. So now that immediately tells me what my hard collinear operator needs to be.
So did you say why that's true again?
So here, this is I'll stick with just this, the field strength. Sort of the simplest operator I know how to construct that's local, right, is just my field strength that has nice gauge transformation properties, right? So this right here is, you know, if I'm going to borrow misappropriate language from conformal field theory, this would be my primary operator. I can't write down anything simpler that is has nice transformation properties under my gauge transformation. I dressed it up with Wilson lines in order to make it gauge invariant. Then I thought through the different components, you know, the n bar perp, n perp, you know, this is way power suppressed, so on and so forth. And I just found the first one that was non-vanishing. And then using the power counting that I had for my derivatives up here, which is the power counting I have for my momenta, that tells me the order that the operator is, which is coming in at order lambda squared. Another way to do this, and this is the way that they would traditionally do it in SCET, is that once you've built up this most simple object, right, you're going to write down what your action is. I don't really want to start writing down the SCET action. And then based on the power counting for your momenta, you'll have a power counting for your positions. Based on all the derivatives and whatnot that's going to sit in that L, I want S to be an order 1 quantity. And that will enable me to figure out the power counting for all the fields inside of my L, because I also know what the power counting of my derivatives are based on the power counting for my collinear states. So that's my very long-winded explanation about why that's my leading power operator. So now I want to figure out what this O hat hard collinear is, right? Well, the simplest thing that I can do, the most basic thing that I can do in perturbation theory, is have an operator which destroys or creates a single gluon that's collinear or a single quark that's collinear. Now, I'm going to need a hard matching coefficient, right? The hard matching coefficient is going to absorb up what is my Born configuration, right? You should think of that as the Born configuration in any hard quantum mechanical fluctuations which preserve my Born configuration. So at tree level, the hard matching coefficient is precisely going to be my tree level 2 gluon amplitude. I'm going to introduce N1 and N2. You should think of N1 as being parallel to Q1, N2 as parallel to Q2. And really, in our kinematics, you can always make this as, this should be true to leading power. But right now, I'm just going to leave them as N1 and N2. It can depend on my soft color indices that I had, S1 and S2. This omega-1 and omega-2, that is the large momenta going into the hard interaction. I said my matching coefficient can be an arbitrary function of this derivative, my normal n bar partial derivative, right? Well, I'm not actually going to write that derivative in there. Instead, I'm going to do a little bit of a trick. I'm going to write omega 1, omega 2. I'll have my b per n1 mu at 0. And then I'll have a delta function like so. So if I did very naively this integral over omega 1, what will it do? Well, it'll just put that derivative up into my hard matching coefficient. And so how do I figure out how many n bar derivatives I need? I'll just do my matching calculation. But my matching calculation will be very simple. It'll be just whatever is the calculation of my tree level amplitude, my Born level configuration. Like so. And now what would happen if, say, I did this? This is going to give me my polarization with my index mu times a delta function like so. Which means when I go to calculate this particular matrix element, sorry, where'd my gauge index go? It'll be like, I have to be now extremely careful about my gauge indices. Say C1, C2. You have to remember this guy has a leftover index here that can contract up into the hard interaction. The leftover index was the index somewhere. Maybe I didn't write it down. It's the index that's sitting right here on my Wilson line, going off to infinity. And repeated indices here are going to be summed, right? So there's going to be a summation between C1 and this guy, and C2 and this guy. When I calculate this particular matrix element, what I'm going to find is epsilon 1, epsilon 2, mu. C in bar dot Q 1 times N1 bar 2 Q2 times N2 S1, S2, A, B. Those are gauge indices with my matching coefficient. And this whole thing needs to be equal to my tree level expression that I had at the very beginning of my board configuration. And that's going to be simple because we know that is true up to power corrections. I can actually put eyes here. So now I can figure out what this C had to be just by going all the way back up. Somewhere it's going to be there. Right here. My tree level calculation is going to determine for me what that C is. I'm just going to factor out these epsilon 1, epsilon 2. I'm going to get a G mu nu here. I'm going to get a mu here and a nu there. And that's my C. And appropriately expand whatever leading power is going to be. Which you can already see because of the perp projections that I have. This particular term is going to drop out. This is going to be my leading power term. Okay. So then that's how I constructed my collinear sector.
Could you please just clean the first line of this thing that you just did, like a few lines back? Yeah, could you a little bit further? Yeah, that line. Could you clean that line up just a little bit? The zero, starting with the 0.
Right here.
The one above it. No, that one, yeah. No, sorry, the one below that thing with the, is that a delta, like, is it a closed parentheses? Just that line that you do starting with 0. Sorry. So that is a delta function in there.
Yes, that's
Okay.
a delta function.
Okay, good.
That is a delta function. Right. And all that happened is that this is just a total momentum operator. So it's just picking up the total momentum of
The
this
delta function has the derivative, partial derivative that's going to act over on that thing.
on my state there. Okay. And now if my state becomes arbitrarily complicated, I'm just going to pick out the n bar component of that arbitrarily complicated state. And it's all going to sum up to omega 1. What is omega 1? That's really the total energy of my collinear sector. That's all it is. Total energy expanded in my coordinates. And I guess here I should have my C1 there. There's really a C1 here. So it's the total operator. I figure out what my hard collinear operator is. I figured out what my soft operator is. Let's just write it all down together. And my hard matching coefficient. And my hard matching coefficient is guaranteed to be gauge invariant because it's only multiplying gauge invariant things, and I'm determining it by comparing it to a full theory calculation, which is also gauge invariant, right? So I don't have to do anything special in order to get my hard matching coefficient to be gauge invariant. I'm doing something suspicious with my leftover color indices. Please forgive me. That's what I did. Nobody call me out on it. When I do the calculation for the hard collinear operator, in order to take the full matrix element, and I didn't do this and I should have, I need to consider just the vacuum expectation value of the solve. And the reason why I need to do that is because I put in indices that contracted into the soft state. Right. Which is fine. There should only be 2 indices on my collinear operator. I mean, in my matching coefficient. There should be 2 adjoint indices on my hard matching coefficient. These guys contract into the soft. These 2 indices contract into the soft operator here. So S1, S2 contracted. These guys are matrices. They now contract back their other indices into the collinear operators over here.
So those are color indices?
Those are color indices. They're all color indices. Global color indices, right? And no gauge transformation properties associated. And now this expression is correct. C1, C2 contracts into these guys. S1, S2 contract back into this. And in particular, this thing has to be an SU in C invariant. It has to be invariant so that this thing is actually gauge invariant at position 0. So that's where this index S1 and S2 is sitting. But that's easy. That just means the unique SU in C invariant tensor I can write down. It's just the delta function. So if I wanted to, I could factor that out to all orders for my matching coefficient and move it over into my solver. The picture that I have, here's my hard interaction. Here's my collinear sector. Here's its gauge length. Here's my other collinear sector. Here's its gauge length. Maybe I'll write it this way. That's a field operator right there. Now here's my soft Wilson lines. So I have a delta S1, S2 sitting here, S1 here. And here I have my C1. Here's my C1. Here's my C2 over here. Here's my C2 over here. And here's my S2. And that gives you the structure of the color flow.
When you did the solve factor, you pulled out a non-dynamical piece that you said went into the hard part, which was like gave a P plus or something. Okay. When you did this, guys, you separated out the hard part from the collinear piece.
Mm-hmm.
Are these analogous steps? In other words, I mean, you kind of factorize the hard part out of both sides.
Yeah, so this is a subtle point.
Okay.
Without knowing it, you just described SCET2, not SCET1.
Okay.
Has to do with the power counting that you assign the softs that I just glossed over. When you're in SCET2, your soft Wilson lines are actually arising out of a matching condition. And you can see this because in SCET2, I'll go ahead and give you the power counting for SCET2. It goes as Q lambda, 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 where this is n bar in per. So that's some soft momentum in SCET2. Now my collinear goes as 1 lambda squared lambda. If I do P soft plus P collinear, I'm going to get a momenta that goes as 1 lambda lambda. That's off shell. In other words, it's not going to scale homogeneously as lambda goes to 0. Another way to see it is that if I look at P soft plus P collinear squared, but this is the sum of both the soft and the collinear momentum. This guy, right?
Yeah.
Is order lambda squared.
Right.
Whereas this term is order lambda. Which means if I had some propagator in my theory, I would expand out this component and I'm now going to be left with something that looks like 1 over my light current direction dotted into my momentum. So when I construct SCET2, I'm actually doing an expansion of my propagators in the full theory, so to speak. And that's going to build up for me my soft Wilson lines. And so there, when I think about the soft Wilson lines in SCET2, since I'm expanding propagators, that means I'm actually generating some sort of matching coefficient. I'm integrating something out, so to speak. SCET1 is different. SCET1, and this is where the top-down view of SCET becomes handy because you immediately confront these issues when you do the top-down view of the construction of SCET. So this is actually how the original papers on SCET did things, not what I did today. Today we were just exploring and trying to find out how does factorization, what must factorization look like? And like I said, I didn't prove anything. I'm just saying if it does factorize, this is what it has to look like based on degrees of freedom, symmetry, and power count. Now, it may not actually factorize. I haven't proven that. But if it does, it has to look like what I just wrote down. That's what I proved. In SCET2, I mean SCET1, I assigned this power counting.
But that's just like columns.
I know. Like I said, at leading power, you can get away with a multitude of cents. In SCET, you see the difference at subleading powers between ultra soft and soft radiation. That's where you're going to start seeing the differences. When I add these two together, I just get back a collinear scaling. And when I want to decouple ultra softs from my theory, you actually have to do a field redefinition. This is the way they do it in SCET1. You do a field redefinition. Because, and it's a similar idea of how I got rid of my N bar, you know, that derivative was troublesome. Well, in these components, which derivative is going to be troublesome? This is power suppressed, so I expanded away. This is power suppressed, so I expanded away. The only derivative that's going to be troublesome on my naive collinear sector It's a covariant derivative that has ultra soft fields in it in the n direction. But we know how to deal with that, right? We get rid of the covariant derivative, and then we'll be left with a normal derivative. And normal derivatives are fine to have in our collinear sector. Right? And when we do that, we're going to get our ultra soft Wilson lines. We'll do a field redefinition, which will convert any ultra soft derivative, field derivative, that can live according to the power counting in my collinear sector. And we'll convert it into some function that's actually now a Wilson line. And when you do the field redefinition, that's what the Wilson lines will come. So yes, depending on your power counting, the soft Wilson lines are either arising out of a matching or they're arising out of the field redefinition. And like I said, this doesn't really matter at leading power, but at subleading power, it does make a difference. And I think, that's all I had prepared for today. So.
Good enough. Officially 6 minutes remaining for questions. And Shaojan raised your hand. You may have to type your question. Anyone in the room have a question?
I don't have a question, actually I have a comment. I really like everything you say, agree with everything you say, especially you say you have not proved anything yet. If it's a then the type of form in this way, we provide the right way to construct software operators. Then I put myself to the shoes of student. Then why should, if I'm dealing with a Higgs decay to multiple gluons, well, gluon, boson, I could not say A and B is special, they will take the lead, rest of that is solved, or rest of that is clear. So what we, at least the way I've been doing this calculation, might be a little bit gap help than say, well, if I look at the diagram and demonstrate, say, particularly, the two gluons, those over, if you say some mass point gluon, exact line, like, maybe I have one more gluons, maybe a real diagram, say, okay, look at the base control. And actually, no problem 4, they have to either solve or collinear given the new contributions, or say, and actually, if I saw a connection to what you here, in the sense that a student, if I put myself in a student too, and say, why should I only concentrate on these? Because you can have another next problem, say, okay, if I look at 3 gluons and the credit is not the angle, then everything will be on that, and that's a problem. So I think it's just
Okay. I will address that a little bit on Monday, because right now I did everything at the level of amplitudes, and that's just to introduce objects, right? But amplitudes are not observables. They're not. So it's when we get to the amplitude squared where we're really going to have to start thinking about how the measurements I impose on the final state is going to select from the operators that I write. Right? And the power of like the effective field theory way of thinking is that by just thinking about the symmetries, degrees of freedom, and the power counting, that gives me the necessary conditions for the form of the factorization. So I can now just start using these rules to write down what the form of the factorization has to be if it does factorize. Right? And that's actually a very powerful thing to do. It really accelerates the process of writing down factorization theorems. We haven't proven it yet, though. There are all sorts of solids.
There's a question on your screen.
You just look behind you.
Yeah. It's great. It popped up over your head.
Is the TMP solve function type 1, type 2? It is type 2. How do I see that? Monday. Why are there 2 soft Wilson lines in the soft operator earlier in the lecture? And why are they time ordered? They're time ordered because I'm doing amplitude factorization, right? And amplitudes really are just time ordered Green's functions that I'm truncating the endpoints on. But since my amplitude is a time ordered Green's function, that means all my operators should be time ordered that I write down. In my collinear sectors, this doesn't matter because I'm writing them basically like just, well, I guess I could put time ordered. There is no case. Technically, that should be But most of the time we don't. But in the soft Wilson line, you would need the time ordering, and you would actually see this when you do the matching calculation. You put the time ordering down, you're going to get particular I epsilons because of the time ordering. And the I epsilons generated in your effective theory better match the I epsilons that are in your full theory, right? And that's why I went ahead and put the time ordering. But you wouldn't see that until you go to loop level. Everything I did here is tree level, so I can get away.
Sorry, Duff, can you elaborate a bit more on why there are two soft Wilson lines there?
The collinear operator that generates multiple collinear.
And let me type.
Yeah, so this is something I haven't done also. Right? I can start thinking about matrix elements like this. And now I could put a P1, P2, PK here. And how would you go about calculating that? Well, hidden inside of here is going to be SCET. There's an action. It's a dynamical collinear sector. So I constructed for you the operator which interpolates. But there's all sorts of interactions embedded inside of here that I haven't constructed for you yet. Now, using the exact same power counting rules that I wrote down, and also my B-perp operators that I wrote down, you can actually write down what is the leading power SCET action. I'm not prepared to do that right now, but I can give you references where it's done. The point is that now, you're going to create your gluon state, and then you have your Wilson line, and now you can have arbitrary interactions where each one of these vertices here is my SCET vertex in my SCET action, right? And eventually they'll create my P1. States. Fun fact. Power. My action for SCET is actually equivalent to just 40. So I can just use my gauge link here. That's the only thing that's going to actually know anything about my new bar direction. And everything else in this diagram I can calculate just using 40s. In the amplitude literature, this would be a splitting amplitude. Which I believe the 1 to 2 is known as free loops. Technically, the 1 to 1 is known as 4 loops. Yeah, I would say the 1 to 3 is known. Which also means all loops. So that's what that matrix element reproduces for. And you can go and actually do the calculation. You look up the splitting amplitudes that the normal perturbative Keystone people write down. And you can calculate these matrix elements in SCET and you find that they produce the exact same expressions.
We'll have to close the session here today, so thank you, Duff. Conclude on Monday.